Gravity, as we've said, is the force that mostly governs the behavior and the motions of celestial objects. And so Newton's theory is going to be the cornerstone of everything we do from now on, and it behooves us to go back and fill in some details and see what more we can get out of this wonderful formulation. And so in this clip, we're going to work through some more detailed calculations applying Newton's universal law of gravity, and along the way learn some things both about astronomy and about gravity and even some math. And so let's proceed. We have things to do. First thing we have to do is reconcile our story about the universality of gravity with the rather simple picture that we've been using so far. So let's understand, when I am standing in the vicinity of the Earth, the actual gravitational force that the Earth exerts on me, tells me Newton's theory, is a sum total of the gravitational attraction of every little bit of Earth. Because gravity is universal, every atom of Earth attracts every atom of me, and I need to add them all up. Now, I'm pretty small, but I need to figure out how to add up the sum total of the gravitational attraction from all different parts of Earth. And so Newton showed us the way to do this, along the way inventing theory of multiple integrals to do it. But what he showed, and we're not going to repeat that calculation for that reason, is that if you just take a round, spherically symmetric shell of mass, so imagine just the crust of the Earth with an empty inside, then the total force it exerts on someone standing over here at some arbitrary point outside, well, if the mass of the shell is m, and my distance from the center of the shell is r, then the force that the shell exerts on a person over here is gm over r squared, and it's directed towards the center of the shell as it had to be by symmetry. The force is the same, therefore, as would have been created by eliminating the shell and replacing it with a mass m located at the center of the circle. Now, if I, on the other hand, ask the same question, and this will become important to us later, about what is the force on an observer here? Well, here again, some parts of the shell attract you this way, some parts attract you this way. The result for the force is striking. The result for the force is that it's absolutely zero. There is no force applied by a spherical shell anywhere on the inside of it. We don't tend to make too many measurements on the inside of Earth, but we are on the outside, and what all of this tells me is that if I consider Earth as a collection of concentric shells, and I consider the full gravitational effect of the Earth to be the sum of all the gravitational effects of each concentric shell, then this has the effect, as far as I'm concerned, of replacing the whole Earth by an object with a mass equal to the mass of the Earth located at the center. And this simplifies our calculation a great deal. Let's see an example of how we use this. So let's go back to figuring out my weight. My mass, you will recall, hopefully hasn't changed much, was 59 kilos. And so to compute the force on me standing on the surface of the Earth, that means my distance from that imaginary mass at the center of the Earth is the radius of the Earth. I will use the astrological symbol for Earth to signify things like the mass of the Earth and the radius of the Earth, because it's simple to produce in tech. And so the force on me is given by Newton's expression, gmm over r squared, where I've replaced the Earth by an object with the same mass as Earth sitting at its center, plugging in the numbers for g, for the mass of the Earth, and for its radius in meters squared. I find, not surprisingly, that when I multiply all of these things, guess what? I found our old friend, mg. This object is what we call the gravitational acceleration on the surface of Earth. And if you wish, then measuring the gravitational constant as Cavendish did, measuring the radius of the Earth, which you can do geometrically, this is a way to determine the Earth's mass. We've computed the gravitational acceleration on Earth from Newton's formula. We know that as I get farther away from the center of Earth, or as I get higher up beyond, into and beyond the atmosphere, then the denominator in Newton's formula becomes larger. That r squared in the denominator, my distance from the center of the Earth, grows, and gravity weakens. It's not that gravity does not exist, of course, beyond Earth, but it is weakened with distance. I want to get a quantitative estimate of this. So let h be my altitude above the ground. This is what Newton's formula predicts for the force of gravity on an object of mass mr, say me. I'm going to rewrite this in a useful way. I'm going to rewrite this as g times the mass of Earth divided by r of radius of the Earth squared. Well, I've divided and multiplied by the radius of the Earth squared, so here I need to put radius of the Earth squared over my actual distance from the center of the Earth squared, and then I'll remember mr. And then I recognize this combination as what we previously called g. When h is 0, this quantity is 1, and I'm back to the surface. So in the second line, I'm rewriting this as my weight on the surface of the Earth times a dimensionless number that indicates how much it's decreased, and then I simplify this, dividing numerator and denominator by the radius of the Earth to get this expression. And the point I want to apply here is that I want to see, this is an exact expression, I want to see if I can simplify it for cases where my height above the Earth is not very large compared to the radius of the Earth. And to the rescue comes, of course, none other than Newton, who derived the following important expression. It is perhaps the only application of calculus we will use broadly in this class, so I won't derive it, but it's a fact that if you take this combination, 1 plus x to a power, and if x is much smaller than 1 in absolute value, x can be negative or positive, then 1 plus x to the power a is approximately given by 1 plus ax. The smaller x and the smaller a, the closer the approximation is. And because I'm not proving it, here's a few graphs that demonstrate this. This is the x-axis. X is running from 0 to a tenth. This is 1 plus x to the a for various values of a, indicated here, running from 5 to minus 4. And you see that as long as x is not too large, this approximation is valid, and this will allow us to simplify many, many calculations in the class. So it's one result of calculus that I want you to accept from me, and you're welcome to test it. Just as I have shown you in this graph, you can get some more examples. So at the moment, let's apply it to this example. So here, h over the radius of the Earth is x, which I'm going to assume is not too large. Remember, a tenth gives me an altitude of about 700 kilometers. And a is negative 2, and so the approximation yields 1 plus x to the minus 2 is about 1 minus 2x. And this gives me the approximate amount by which the force of gravity decreases as I elevate myself to an altitude h above the surface of the ground. Of course, when h is 0, I reproduce my weight on the ground. And this is valid so long as your height is negligible or small compared to the radius of the Earth. Let's apply what we've learned to understanding potential energy in gravity. We've already had an expression for potential energy, mgh, but this was valid as long as we assumed the force of gravity was constantly mg. We saw that as you get farther from the center of Earth, the force decreases. Every height gain costs less energy, and therefore, taking that into account, we find an exact expression. This is the exact expression for gravitational potential energy in Newtonian gravity. These two do not look the same, and I did not derive this because it requires some calculus. Let me convince you that they're not as different as they appear, another opportunity to use some skills we've developed. So let's write the potential energy using the correct expression at an altitude h above the Earth's surface. So I write, for distance from the Earth's center, r plus h. And as always, I rewrite this by scaling it to a known quantity, and that would be this one. This is your potential energy on the surface of Earth, and then I need to write this dimensionless quantity, which gives me the scaling. And again, I divide numerator and denominator by r to get minus g mm over r times 1 plus h over r inverse. And another opportunity to apply Newton's formula. A is negative 1, x is your altitude. If your altitude is smaller than the Earth's radius significantly, then Newton's formula applies. That replaces this by 1 minus h over r. And I will do the calculation in my head, and the 1 is easy to do. It's this constant number. And then minus h over r gives me a positive contribution here, an extra factor of r in the denominator, gm over r squared mh. And I recognize two things here. One is this is independent of your altitude, it's just a constant. And this object here is g. So the difference between this exact quantity and our approximation for h that is significantly smaller than the Earth's radius is just a constant shift. We said that a constant shift is irrelevant, and so this formula is as valid as this for h much smaller than the radius of Earth, and then at higher altitudes this becomes valid. We can see the mathematical calculation graphically here. This would be mgh. This is the exact potential energy. The graph shows us two salient properties. One is the potential energy is always negative. That's just a choice of our constant that we added. It becomes closer to zero. It increases towards zero as one gets farther from Earth, so it approaches zero at infinite distance from Earth. Near Earth it increases. mgh and minus gmm over r are not the same, but if one shifts this down by an appropriate constant, then one sees that as long as h is much smaller than the radius of the Earth, you get a good approximation. The statement oft heard that there is no gravity in space, we've seen is patently false. The Earth's gravitational attraction extends throughout the universe, but it does weaken with distance. And so perhaps a corrected version that sometimes one hears is that astronauts in the space station are weightless because the gravitational force of Earth is weaker at larger distances from the center of the Earth. Here we see Stephen Hawking weightless. No. The space station, as we have said, orbits at an altitude of about 400 kilometers, so we can compute the force of gravitation. We can compute the weight of an object, say myself or even Hawking, at an altitude of h above the Earth. We found that the approximate version for the force of gravity for altitudes h smaller than the radius of the Earth is this formula. This makes it easy to plug in the numbers, and you find that in the space station, your weight is in fact 87%. In other words, the force with which the Earth attracts you is 87% of what it would be on Earth. Why then are astronauts weightless in the space station? Why is Hawking weightless in this picture? Stephen Hawking is far too important to humanity to allow him to travel to space and take the risks of real space travel. Hawking is weightless because in fact he is accelerating towards the ground with an acceleration that is essentially g. When you are in free fall, there is no gravity, and there's a beautiful demo that explains this. We said that all you have to do to be weightless is be in free fall. So what I'm going to do in this demonstration is I'm jumping off a box. I'm jumping in ultra slow motion because we filmed the video with a high-speed camera and have slowed it down further. And as I fall, to demonstrate that I'm really weightless, I'm dropping this little white ball. And what you see is that as I drop the ball, of course the ball's falling, so am I. To my eyes, the ball is hovering in front of my face and it's not moving. And it won't stop falling in concert with me until my feet hit the ground. You can tell exactly the moment when my feet hit the ground, because that is the moment when the ball is no longer level with my nose. Well, I hope you found that amusing. What we saw is that when you are freely falling, you experience no gravity. A ball you drop will hover in front of your face. Had I thrown that ball up, it would have, relative to my nose, moved up at a constant velocity. And this is important because in space there are no floors for your feet to hit, and so everything is in free fall. For example, the Earth, as it orbits the Sun in its circular motion, is in free fall under the gravitational influence of the Sun, which means that when studying the motions of objects near Earth, we can completely ignore the Sun's gravity. We are all in free fall towards the Sun. Really? Almost. The reason we are only almost all in free fall towards the Sun is because we're all actually held together by staying on Earth, so we're all falling towards the Sun with one constant acceleration, And that could not possibly be the free fall acceleration towards the sun at all the positions we are, because at different positions, the free fall acceleration towards the sun is different, depending on your distance from and direction to the sun. These differences in the gravitational free fall acceleration at different points of an extended object will lead to forces, tidal forces, we'll see why we call them tidal forces, that account for the differences in gravitational acceleration between different parts of an object. These differences manifest themselves in leftover gravitational forces. Like all gravitational forces, they are proportional to your mass. So the tidal force on a refrigerator is more than the tidal force on a tennis ball, and they're given by your mass times the difference between the gravitational acceleration towards, say, the sun, where you are, and the acceleration with which, as a denizen of Earth, you actually are falling onto the sun. That would be the gravitational acceleration towards the sun as it applies at the center of the Earth. This sounds a little bit confusing, and like many things, can be clarified by a good calculation. Let's turn to that. Let's do this, and let's do the calculation. So in this image, we have the Earth over here. The sun, I'm going to assume, is way over there in the left-hand corner and way outside the image. And because the sun's gravitation applies a force to the Earth given by F equals g times the mass of the sun divided by the distance to the sun squared times the mass of the Earth, the entire Earth is accelerating to the left towards the sun with an acceleration given by this is equal to the mass of the Earth times the acceleration of the Earth, and I can, as always with gravity, cancel the factors of the mass of the Earth. And so what I find is that the entire Earth is accelerating towards the sun with this acceleration, where the distance to the sun I'm going to take as always as the center-to-center distance, because that is what Newton taught us to do with spherically symmetric objects. Now, the important thing is the entire Earth is accelerating to the left with this acceleration, and because this is the acceleration of free fall, gravity would cancel, except that if you are sitting at this point on Earth, you are a little bit nearer the sun than the center of the Earth by a very small amount. This is 6,400 kilometers. The distance to the sun is 150 million kilometers, but it's a difference nonetheless. So the gravitational acceleration towards the sun here is a little bit larger. And so the gravitational acceleration towards the sun at this point is larger because you are closer to the sun. Indeed, the denominator for computing here should be decreased by the radius of the Earth. Similarly, the gravitational acceleration on the far side of the sun will be smaller than the value in the center of the Earth because you're at a larger distance by the radius of the Earth. Now, the radius of the Earth is, of course, much smaller than the distance to the sun. This gives us a wonderful opportunity to apply our approximation that we learned from Newton. We do the usual steps. We write here, pull out d squared. I'll shortcut the next step. We will get 1 minus r, radius of the Earth, over distance to the sun, to the power minus 2. X is the small quantity, radius of the Earth divided by distance to the sun. A is negative 2. And the result is gm over d squared, which is simply A. And then times 1 plus 2 r over d. And so this is our approximate value, valid because the Earth is much smaller than the distance to the sun, for the value of the acceleration of gravity on the near side to the sun. And we can make a similar calculation over here. The difference will be this plus sign will turn into a minus sign when we multiply it by minus 2. So we can write the acceleration over here in a similar form. Now this suggests rewriting this as a sum of two terms, the acceleration with which the Earth approaches, and then an extra little bit. So an object over here has a free fall acceleration towards the sun that is larger than this one by the amount of this little yellow arrow, which signifies A times 2r over d. And similarly, an object on the far side of the sun has a gravitational acceleration towards the sun that is less than the acceleration with which the Earth moves towards the sun by approximately the same amount, to this order of approximation. Now, one can apply a similar logic to these positions on Earth. their distance from the sun to first order is the same as that of the center of the Earth. So one asks, why is the gravitational acceleration here different from that at the center of the Earth? Well, that is because, to a very small extent, the direction from here to the sun is not the same as the direction from here to the sun, as these arrows, in again a grossly exaggerated version, demonstrate. This would have the sun about here. The sun should be very far, so this angle should be tiny. But again, I can rewrite these as the gravitational acceleration at the center of the Earth plus a small correction. And so the net result is that the gravitational acceleration with which the Earth is moving towards the sun, that part of the sun's gravity is cancelled by the Earth's motion. But the leftovers, these yellow little differences, are not cancelled. So if I put those differences back in their place, I see that the net result is that the sun exerts a small force upward away from Earth on this side of the Earth, and a small force upward away from the Earth on this side of the Earth, and a small force downward on this side of the Earth. In other words, the sun is doing its best to smush the Earth into this oval that is elongated in the direction of the sun. And so, of course, the Earth is kind of a rigid object. The sun cannot manage to deform the Earth, but the Earth is under some kind of tidal stress. Now, before we get too excited, let's figure out how strong this force is that we've calculated. Again, the magnitude of the force depends on what it's acting on. These are all accelerations. So imagine a 1 kilo rock and figure out the net force that this has, or better yet, compute an acceleration and compare it to the acceleration of gravity. So we know, is this rock essentially rendered weightless? Is it lifted off the Earth by these tidal forces? So we can do the calculation. We have here all the quantities we need. The tidal acceleration due to the sun is the difference, that little yellow difference, which was 2gm over d squared times r over d. The salient point is that because I have 2gm over d squared times r over d, this decreases with distance from the sun like the third power of distance. Remember, the gravitational force itself decreases like the second power. And I want to compare this acceleration to something I know, so I will do the usual scaling trick that I like to use. We'll try to pull out a factor over here of the mass of the Earth divided by the radius of the Earth squared. I didn't have the mass of the Earth, I had the mass of the sun, so I get one factor here. I had the radius of the Earth divided by the distance to the sun cubed, so I get a scaling factor. Notice I have an acceleration that is known. This is our friend g. These are dimensionless factors, so I'm relating an acceleration to an acceleration. And plugging in the ratio of the sun's mass to the Earth's and the cube of the ratio of the Earth's radius to the distance to the sun, I find that the acceleration, the tidal acceleration due to the sun, is very small. It's 5 parts in 100 million, the acceleration of gravity. So no, it is not about to rip the Earth apart. This is the tidal acceleration due to the sun. What else might exert a tidal influence on the Earth? Well, the second object that we might imagine would be the moon. Now, the moon is much less massive than the sun, but it is closer. And so, because of this third power of the distance, one might imagine that the tidal force generated by the moon might be comparable to that generated by the sun. And indeed, a simple scaling argument tells us that to get the tidal acceleration due to the moon relative to that from the sun, I multiply by the ratio of the masses and the ratio of the distances to the power -3. Plugging all the numbers in, I find that in fact the tidal acceleration due to the moon is approximately twice that due to the sun. So the dominant tidal effects on Earth are lunar tides rather than solar tides. But solar tides are not negligible. They are a 50% effect. The net result is a combination of the two. Let's take a look at what that does. So here we see the Earth and the moon, of course, drawn way too close to Earth to be to scale. And we see the elongated shape into which the moon is attempting to draw the Earth. Again, exaggerated way out of proportion. Remember, though, that while the Earth is rigid and unable to respond to this tidal pull, except very slightly, because it's a rigid rocky object, there's a soft component of Earth, namely the water. So the surface of the oceans will deform in this direction, ever so slightly, again, not to this extent, but there will be a high tide on this side of the Earth and a high tide on this side of the Earth and low tides at these points because of the tidal deformation that we discussed. And of course, as the moon orbits the Earth, the tidal bulge will point towards the moon, and as the Earth rotates once a day, each point on Earth will have 2 high tides and 2 low tides, and these because you pass through these 2 points and these once a day, and because of the moon's motion along the celestial sphere, tides will repeat not every 24 hours, but every 24 hours and 44 minutes, because the moon advances by 44 minutes relative to the sun, remember? And so, indeed, if you look up tables of tides, you'll find the tides repeat every 24 hours and 44 minutes. This is because they are associated to the moon. But there is another effect another 2 effects that come into play. One is we can include the sun. So in this picture, the sun is way off to the right. The sun is attempting to extend the Earth as a horizontally extended oblong, whereas the moon attempts to draw the Earth to whatever direction points towards the moon. When the moon is full, Earth, sun, and moon are in line, and the sun's deformation, the moon's deformation, are in exactly the same direction, we get very, very exaggeratedly high tides. They're called spring tides. When we have a quarter moon, the moon is elongating the Earth this way and the sun this way, and the tides are diminished. We call them neap tides. Tides are very weak at quarter moon. And of course, when we get a new moon, again, the moon and the sun are elongating the Earth in the same direction, and tides are stronger. So tides are strongest at new moon and at full moon. Those are the spring tides. Tides are weakest at quarter moon. Those are the neap tides. And Newton's theory makes easy sense of all of that. And then there's another effect that we can take into account. The Earth rotates. What the Earth's rotation does is, as the moon creates a bulge of water, the rotation of the Earth, which is much faster than the moon's orbit by a factor of 30, remember, drags this bulge so that water that was raised here is actually over here. This means, farther to the east, this means that the high tide bulge is a little bit to the east of the moon, which means that high tide where you are is a little bit later than the time the moon crosses your meridian. It also has other implications, which we'll discuss momentarily. But these are the 3 effects that this demonstration shows very convincingly. To summarize what we've seen, the moon attempts to deform the Earth. It succeeds in deforming the water in the oceans, so there's a bulge facing the moon. As the Earth rotates, the bulge moves around the Earth, so everybody gets 2 high tides and 2 low tides once every 24 hours and 44 minutes. So the time between one high tide and the next is in fact about 12 and a half hours rather than 12. The Earth's rotation drags the bulge to the east, so therefore it lags the moon. Like everything else in that image, the lag was way exaggerated. In fact, it turns out to be about 3 degrees or 12 minutes. Now, in addition to the moon, the sun exerts a tidal force directed towards the sun with about half as the strength as that of the moon. At full or new moon, these act in concert, creating the intense tides we call spring tides, which have nothing to do with spring. Whereas at quarter moon in either direction, the sun's deformation counteracts the moon's deformation, and you get the relatively weak neap tides. Cool, something we understand. Even more consequences of tidal forces. The moon is not able to deform the Earth, but when the moon formed a long time ago, much closer to the Earth, we'll see, and molten, it was soft and closer to Earth, and the tidal force of Earth, remember, at a closer distance with a mass bigger than the mass of the moon, you get more intense tidal forces. The tidal forces of Earth deformed the moon so that when it solidified, it froze with a permanent bulge. The moon is not quite round. Now, the tidal forces act to keep this bulge always aligned in the direction of Earth. We call this tidal locking, and this is the reason why, as I told you a long time ago, when we look up at the moon, we always see the same side of the moon. There is a near side and a far side to the moon. What locks the moon's spin period about its axis to its orbital period about the Earth is tidal locking, and this is a phenomenon we'll see before. Moreover, since the tidal bulge on Earth is being dragged to the east of the moon, the tidal force from the moon attempting to align the tidal bulge with the moon is actually trying to slow down the rotation of the Earth. Think about it differently. There is friction between the tidal bulge and the rotating Earth because the tidal bulge cannot keep pace with the rotating Earth. It's held locked 3 degrees away from the moon. What this is doing is it's slowing down the Earth's rotation. Yes, the Earth's rotation is slowing down. Look, but Ronan, what about conservation of angular momentum? Well, angular momentum is conserved. The way it's conserved is that that same bulge acts on the moon to, in fact, sling it faster along its trajectory, so that the moon is being accelerated, and as it gains angular momentum, it's actually moving to higher orbits. So the moon is actually receding from Earth. This is an observation first argued strongly by George Darwin, son of the famous Charles Darwin, in 1898, and was the reasoning behind his theory that when the moon formed, it was indeed much nearer Earth. And as we will see, that coincides with modern theories. We think that the moon formed much closer to Earth. And these were conjectures until the Apollo missions left reflectors on the moon, enabling us to make a very precise measurement of the distance to the moon. And indeed, we can now verify experimentally that the moon is receding from Earth. So remember, it is now exactly the angular size of the sun in the sky. In a few millennia, total solar eclipses may be a thing of the past. So, we've worked pretty hard, but we're getting somewhere. Understanding universal laws has given us a unified understanding of many, many phenomena. So we understand tidal forces, and remember, in space, nothing is held up, everything is in free fall, everything is in orbit around everything else, and so tidal forces are extremely important. This is very nicely evident in this beautiful image of M51, the Whirlpool Nebula. And what we see is that these are in fact 2 galaxies that are in the process of colliding. Galactic collisions are slow and rather delicate, but we see that there's a tail of stars from this galaxy being dragged out towards its neighbor by the gravitational force. And now that we understand tidal forces, it's not surprising that there is an equal tail being dragged out by the same tidal forces, since these are in free fall about each other. On the other side of the galaxy, tidal forces are approximately symmetric. These are falling in because the gravitational acceleration is larger than that with which the galaxy is falling. These because it's smaller. The net result is the galaxies being stretched in both directions. So understanding the uses and applications of F equals ma is a very powerful tool, and we're going to continue to apply it as we go along. And what we're going to turn to next is understanding a little bit more about the forces in nature beyond gravity. What else is there? And something about the M, something about the structure of the matter upon which these forces act. This will be important for understanding the structure and workings of various astronomical phenomena. And so that's what we'll turn to in the next clip.